K-means clustering is a quintessential introductory algorithm for machine learning. Join me today as we build it from scratch and learn some tricks along the way. Welcome, I'm Gregory Topline with GNT Learning. On today's episode, I'm going to help you implement K-means clustering from scratch. Now, K-means clustering is a very popular algorithm for getting started, and there's a lot of reasons for this. One of them is that it's a really great introduction to the basic way of thinking about complex arrangements of numbers and high-dimensional vectors. This is where Numpy math comes in very handy. It's also a great way to start asking deeper questions about things like what is distance and how do you want to define the relationships between different types of data. To that end, we're going to assume today that you have a basic understanding of what K-means clustering is, and you just need a little help with the implementation itself. Today we're going to start with an empty notebook aside from imports for Numpy, which is going to be doing the heavy lifting of the math for us today, and for a PLT to help us do some plotting to visualize what we work on. Our goal today is to build up everything from scratch. If you wanted to go all the way to not even using Numpy, you could do this in plain Python alone. It's just that every Numpy line of code would have to be replaced by 4 to 5 lines of Python code with a loop to do the same equivalent thing. Before we can get into the K-means algorithm itself, we need some data to work with. To that end, we're going to generate a set of random data points. So we need to make some decisions at the beginning here. First of all, how many random data points do we want? We're going to go with 20. And how many features should our system have? I'm going to say 2. Here, the features mean something like, if you're talking about demographics, it could be age, weight, height, gender, ethnicity, etc. of a person. So this is just 2 descriptors of a person. And we're also going to go ahead while we're here and define the number of clusters we're going to be using ultimately as k equals 3. We can then generate our data at random using np.random.random. And this is a very common error that people don't catch. There's 2 randoms there. And then we can define our set of random data points for number of samples, comma, number of features in those samples. And doing this itself does generate some data at random. So that we can have the same data and some kind of consistent reruns of our code, we're going to go ahead and do np.random.seed at the beginning as well and set our initial random values. This means that if we rerun this code, we'll get exactly the same random values every time, although they are still just random values, they're consistently the same random values. Secondly, even though we've generated data in X, it would be nice to visualize and see what's going on with it. If we just look at the raw values, it's not going to seem like much. So we actually want to go ahead and just plot it using plt.scatter. Right. To do that, we need to plot values on an XY coordinate axis. So the values on the X axis are going to be determined by the first feature or 0th feature in our data set, and the other points will be defined by the first column, if you will, of our data. Implying this, we can see that this is what our data points look like. Now, in principle, the algorithm we're going to write today generalizes to any number of features. However, for convenience of visualization, we're going to keep it to 2 because a 2-dimensional set of features is something we can actually visualize and see how our results look. Now we have some data to work with, let's talk about the actual algorithm we're going to implement. Well, there's a couple steps to the K-means algorithm. Let's take a moment to prototype out the code so we know roughly what we're trying to write. Well, to start with, we know that we are going to have a loop here. And during this loop, we're going to continuously make updates to what's going on until we reach some sort of convergence. And we'll talk about what the convergence means later on. Inside that loop, we have 2 parts. The first part is updating our understanding of which points belong to which cluster. I'm going to call this update cluster membership. The second part of this loop is that we're going to update our understanding of what this is a cluster. In this sense, we're going to update the center of the cluster, and that's really because of how K-means works, that we define a cluster by its center. So update centers. Then we just go back and forth in the loop, updating the centers, updating which points belong to the cluster, updating the center, back and forth until eventually we can reach that convergence. Now for this to work, we have to have one other little piece at the front, is we need to initialize an initial guess for the centers. Without an initial guess for the centers, we can't define our initial cluster membership. We have several little pieces here. So rather than try to write the whole thing in one giant go, let's take care of implementing each of these individual little pieces, starting with initializing the centers. So init centers. The way we're going to do this is by selecting some random subset of points from our add data to be our initial guess for cluster centers. We can do this with np.random.choice. And it's going to take 3 arguments, n, k, and replace equals false. N corresponds to the number of points we have, in this case 20. And we're going to say we're going to use one of those 20 points at random as our cluster center guess. K is the number of clusters we need to initialize, in this case 3. And replace equals false, it just guarantees we don't pick the same point twice. We run this, and we see that we get back several points that we could use. Now, there is an issue here is, well, what do we actually want in terms of centers? We actually want to know the physical location of the centers. So we've chosen the points we want to use to get those centers, but this isn't their coordinates themselves. And this is one of the first places where Numpy really gets handy, is that we can use the open square bracket syntax in order to grab multiple points at the same time. So I can just take this entire piece of code here and do this in order to grab the coordinates for 3 points at random. And let's go ahead and save this to our variable centers. Great, now we have some initial centers to use. Now there are other ways of choosing centers. The most notable and actually used way is a method called k++, which does this in a less than completely random way, but has the same basic idea of choosing a subset of the points in order to initialize your guesses for the cluster centers. Now we have our cluster centers in hand. Let's go ahead and move on to the next piece, which is updating cluster membership. We need to know for each point which center is the one that is closest to it. To that end, we need to define what closest means by measuring the distances between points and centers. Let's start with a simple case of a single point and a single center. Right. So if we just do subtraction here, we see that we can subtract the distance between a point and a center and get the raw difference in the coordinates. We want an actual distance, so that's easily enough done by squaring these values and then taking the sum of them, and then finally taking the square root of that. So this is the quintessential definition of distance, or Euclidean distance, which is the distance we normally think of day to day, and will tell you how far apart these 2 points are. Now, there are other measures of distance out there. For example, there's a Manhattan distance, which would not have the to the power of 2 and to the power of 0.5 here, and would just sum up the differences among the different dimensions. The Euclidean distance, the one defined here, is the one we use day to day and is the way you actually measure distance in the normal world. But there is no particular reason when you're doing Kmeans that you have to use the Euclidean distance. That's what we are going to stick with today, though. We've shown that we can do it for one center and 1 point, so how do we generalize this to all of them? Well, we could just do a big loop over all this, and that would work, but it would take a while to run, and it wouldn't be very efficient. We can use the power of Numpy here to expand this to do more points at once. For example, we can take all the points and subtract them, or find the difference between them, and one particular center. Right? And voila, it works. And the reason this works is because of broadcasting. Under the hood, you can realize here that X is itself a 2D array. It has both a number of points and a number of features. Centers, 0, is just one particular point. So it's really a 1D array. When you have a 2D array run into a 1D array in Numpy, it automatically attempts to broadcast it and expand this 1D object into a 2D object that matches so they can repeat the operation along it multiple times. And this works just fine in the case here. And so from here, we can then do the distance calculation. And it looks very much the same. So you have the values. We can go ahead and square them. All right, we see that part. That part works fine. But then we come to the part where we do the summation. And we realize we actually don't want to do a sum over everything. We actually don't want to get back a single value for distance. We want the distance between every point in that center. So we have to use the optional argument in sum called axis. An axis will allow us to define which axis is going to be eliminated or reduced out of our calculation. So before we had this input that had multiple rows and 2 columns, what we want to do is choose the right axis to eliminate the piece we want. Let's start off with making the wrong choice of axis equals 0. So here, when we say axis equals 0, we're summing over all of the points instead of all of the features, and we get back 2 values. That's not what we wanted. We should have had one result for every single point. And so just doing a quick check of plugging in a value and looking at the picture here allows us to see, oh, we're doing something wrong. Just taking a moment to stop and think about the shapes, rather than necessarily trying in your head to make sure you're thinking about all the axes correctly. Just do a very quick dumb check. Oh, that's not right. Okay. So we do axis equals 1. We see we get a 1D array again, but now there's one value for every single row, or for every single input we had n in our input x. Okay, that worked beautifully. We went from doing 1 point to doing multiple points. Can we just do everything at once? What if we just say x minus centers? And we find out it doesn't work. What happened? Well, broadcasting no longer was able to automatically figure it out for us. Before, when we had a 2D object and a 1D object going through subtraction, it was able to figure out that, okay, I expand the 1D object into a 2D object, everything's fine. Now I have two 2D objects. And I can get this to work, but I have to go to higher dimensions, and it's not very obvious in what way it should go to higher dimensions. All right, to explain that a little more clearly, let's look at this part up here. We had two 1D objects that we then combined together and then summed over to reduce to a single value. Here, we did a combination to create a 2D object that we used sum to reduce to a 1D object. Well, our final output is going to be a 2D object, so this means that the output of this has to be a 3-dimensional object that we're going to sum over. Without getting too far into details of thinking about higher dimensional shapes, let's just say that we can, for today, solve this using a reshape command where we extend this into higher dimensions, and in doing so, we're setting Numpy up to be able to figure out for itself how to do the broadcasting. The key, really, is that it needs to know which dimensions correspond to each other and which ones are doing cross interactions. So we have n is going to be in a cross interaction with k because they don't line up in the shape, but the p are describing the same thing. And by doing this little piece of reshaping, we can get a 3-dimensional object that we can then repeat the same style of code we had before on. And let's do a little writing here. Dot sum axis equals now 2. Right, and start at 0.5. And that will give us the solution for this bigger problem. Now, we don't want to belabor the details of this exact solution here, because while it is possible to do it in one step like this, there is a problem here. And that problem is that in the middle, we're creating this 3-dimensional object. And if n and k are large, or p is large, sufficiently large, this becomes unwieldy, becomes too large to fit in memory. And so for some data sets, this just does not work as a viable solution. It does show, however, that in principle in Numpy, you can expand it, and if your data set is small enough, you can solve this distance calculation in a one-liner like the one shown here. The slightly more practical solution is actually to go back up here and to use this solution and loop over the values. So let's go ahead and look at how that looks instead. So I'm going to copy this and come on down. Now, the way to loop over this in order to turn this into a general solution is we first have to initialize some empty set of data to hold our information. In this case, we'll use np.zeros, and we'll set it to the size we're going to want. So we're going to have the distances between every input n and every cluster center k, so we need an n by k object. From there, we can then loop over all of our cluster centers, okay, and perform this calculation. Now, here we did it with the value of 0 is just for everyone in general. Now we make it a general solution. And then we need to solve, or rather save, our solution to the appropriate center as we go. So in this way, we say for all the value points n at the same time, we're going to update the values for a specific cluster, k. So the second index in distances is k, and in the centers, we're going to grab one at a time. And we can go ahead and do this and show that distances gives us back the same values as we had above, if we remember to actually include our 0.5 here at the end. All right, so we see that this generalized solution gives us the same answer as our specific solution where we loop over them one at a time. Now, this is a perfectly valid way to do it with just Numpy. If you're allowing ourselves to use a little bit more tools, we can import a helper function from SciPy. So we'll go ahead and just show that off as well. So from scipy.spatial, .distance, import cdist. Okay. Now, this cdist method allows us to do essentially the same thing as is shown in cell 19. So cdist of x, comma, centers, and run this, and we see we get back the exact same solution again. Now, this cdist method is a very helpful wrapper of Numpy that's essentially doing the same calculation as the one here, as opposed to the 3D one that can have an issue with memory size. Now, there are some advantages and disadvantages to using this. I mentioned before that the distance we're calculating here is Euclidean distance, which is the default that cdist uses. cdist does support Manhattan distance and a few others. However, you are constrained to the methods it has of solving it. If you decide you want to do something more creative or very interesting and different with distance, there's a lot of other things you could, in fact, define that cdist is not going to support directly. And so it's important that you are able to reach down and do this at a little bit lower level yourself in case you need to do something that requires you to explore something a little more novel or interesting. Now, any of these methods would work for what we're doing today. For convenience and readability, I'm going to stick with the cdist solution as we move forward. So I'm just going to set distances equals to cdist. And I'm just going to go ahead and do a kernel restart run all at this point to make sure we haven't made any little mistakes or have little bugs along the way. And it is a good practice when you're doing lots of little back and forth to make sure your code is actually consistent the whole way through and you don't have any problems. All right. So now we have distances as defined by the cdist function. Stepping back for a moment, we just went on a long tangent to understand distance calculation. But what was the goal we were actually trying to achieve? We were trying to figure out for every single point in our data set what is the closest center. And we need the distances as our metric for defining what closest meant. The closest point is simply the one whose distance is the minimum. To do that, we can simply turn to argmin. NP argmin allows us to find out for a set of points, set of values, what is the index of the smallest one. In this case, we want to know that value for every single row or first dimension in our x value. And so we want to reduce out the answer per center. So we need to set axis equal to 1. And this will tell us which point is the closest. All right. I'm going to go ahead and call this closest equals. And this is, in 2 lines of code here, the first chunk of the inner loop of our function. Now, the second part of our update is we want to go ahead and understand what is the new estimate for the mean of our cluster now that we've updated what points are in the cluster. To do that, we need to grab all the points that belong to a particular center, particular cluster, and find the average position. How do we grab those? Well, the short answer is that we can use closest equals a value to see whether or not that index corresponds to that cluster. So we can see here that the last point corresponds to cluster 0, and so does this point here, and so does that one. And then we can use the x open square bracket syntax to grab the values that correspond to those points. So in this way, we're able to, again, leverage some of the power of Numpy to grab multiple points at the same time. And, simply enough, the mean of these can be calculated exactly using mean. Again, we need to provide an axis argument. Now, there's been a lot of axis arguments as we've gone back and forth here. And the general thing to keep in mind is whenever you're doing something that reduces the dimension of the system, a sum or a mean or an argmin, the axis you're defining is the axis that is going to be removed when you do the calculation. So in this case, we had multiple points and they each had different values. We wanted to take the mean over those different points, which was the first dimension or axis equals 0 of that data. Now we have the answer for a particular center. We can loop over this the same way we showed above, of looping over the distances to calculate them over all the different clusters. So let me just write that out so it's a little more easier to understand. So we can say for I in range k, all of our clusters, we can go ahead and say that centers for that cluster for all the features is equal to the value we have above. I can actually just copy and paste this here as long as I am careful to make sure I change this equals 0 to equals I. And let's just go ahead for completeness here and just show what our new centers look like. And we see we've able to calculate a new set of centers describing where those points are. So now we have the different pieces of our code kind of put out there, but let's kind of get them all together into one place. All right, let's go ahead and scroll up and grab our initialization right here. Okay. Then we're going to go ahead and grab the first part of our loop, or our inside of our loop. All right. And we need to put this in a loop here. So let's say for iteration in range 10, we talked earlier about we need to do this until it's converged. We'll come back to that convergence question in just a moment. For right now, we're just going to make sure all of our pieces run together. All right, so we got the first part of our algorithm, and then here is the second part of our algorithm. And one little extra piece we're adding, just because this is a demonstration, is we're going to go ahead and put an np.random.seed in at the top here, because we want to make sure we have the same values every time we run this, so it's repeatable. 4, 1, 6, 6, 6, 5, 9. And if we go ahead and run this, we will see that, well, it ran, but it didn't give us any output. So sure, the algorithm is running in theory, but it'd be good to monitor it in some way to understand what's going on. So what are we trying to do? We're trying to put points into clusters. So maybe the most useful thing to see would be what the centers, or what those clusters are for the membership. All right, so we're going to go ahead and print the closest. And we're going to have to go ahead and initialize this so we don't have some issues later on. So we'll say closest equals np.zeros n.asType int. Okay, so now if we run this, we can see, a little bit of a mistake on my part. I miscopied something here. I need to grab the centers for the init. Not sure what I grabbed there. Now if I go ahead and actually run this, okay, we can again see that we get the centers as they evolve over time. And we see that we actually slowly do get changes. But again, it is hard to see what's going on line to line, but there are little changes continuously happening as we adjust what points belong to what cluster. How do we know if we converged? Well, we need to, instead of just doing a fixed number of iterations, decide when this value stops changing. There's a couple ways you could write this in terms of code. One I prefer to use here, and this is a style choice, is to just say while true and add in a conditional statement on which I break. In this case, I want to break whenever the set of values closest is the same as what they were in the previous iteration. To do that, we do need to initialize this value here. So we're going to go ahead and say old closest equals closest. And we go ahead and give that a run. And we see that this continues until it eventually stops at some value, which is different than the previous, but it didn't run forever. It stopped because eventually these things came out the same. Now just a little bit of a Numpy side point here, is that Numpy, when you do this equals equals, compares things value by value rather than as a whole. And so this actually returns, this inner part, a list of true and false values. So we need to see that they are all true in order to know this condition has been met. Second thing here, this is a pretty important one, is there is actually a bug. And it's fairly subtle in the sense that this piece of code itself, in of itself, works fine. However, if you begin modifying it, you might run into the issue that this is not a good piece of code. The problem here is I'm setting old closest to be equal to closest. This is not like saying a equals 3 and we're getting an integer value and assigning it here. Instead, we're saying old closest is exactly the same object as closest. So by definition, they're going to be equal. The only reason it happens to work here is because we overwrite closest completely instead of updating it incrementally like we were in our previous calculations for center or distance. Whenever you need to compare a new value to an old value, you almost inevitably need to copy. And if it doesn't cause an error, it's only by luck that you happen to not get an error with what you were doing. So we're going to go ahead and put .copy there when we run this. Now that we have something that converges, let's go ahead and visualize our results. All right, we're going to go back down to using plt.scatter again. And this is going to be essentially the same code as we had before, where we want to look at all of our data points and put them in a nice little plot. But this time, we're going to go ahead and color them by the cluster that they are part of. C equals closest. All right. And doing that, we see our data is arranged into 3 nice little clusters, one yellow, one blue, and one purple. And to first approximation, this looks like it is doing a reasonable job of clustering. So this is a sufficient little check for the moment. Now, Our notebook here is kind of a running mess of different little chunks of code. Kmeans is an algorithm. It is a clearly defined input-output situation where you give it some information, you get something else out. Not a rambling Jupyter notebook. So let's collect all our information into a nice defined function that we can deliver. To do that, we're going to go back up and we're going to do a little bit of copy-paste here. We're going to grab this bit of code we've been working on and come down here and define a function around it. Okay. So for this function, we're not going to use the random C. We're going to let this work however it wants to. We're going to call this function Kmeans, and it's going to take two inputs. One is going to be the data set it wants to work on, and the second is going to be the number of clusters upon which we wish to work, or create rather. All right. Now, go ahead and come down and scroll this over. Now, what are the other variables in here that we need? And the only other one that actually survives is n. What was n? N was the number of points in our data. So we can get n from x.shape 0. We also don't want to be printing a bunch of information to screen all the time. Instead, we want our function to just return a final result when it's done. So we're going to go ahead and return both the closest as well as the centers themselves. Go ahead and define our function, and then let's see if we got everything working correctly. So we'll say labels, comma, centers equals Kmeans x, comma, 3. And let's go ahead and print these results so we can actually see them. Centers. All right. And this looks like a reasonable solution. Indeed, we can go ahead and do a little bit of extra work here and say, okay, what if we change this to 4 centers? Does it still work? All right. We can then go back and take this information and plot it and do some other visualization to get some decisions to see if we think we like the result we have. And in general, this is the solution to the Kmeans algorithm implemented with using Numpy only or SciPy if you're willing to get cdist as opposed to add 3 or 4 lines to do it a little more manually. So overall, we've shown how to implement the Kmeans algorithm from scratch, but there's a lot of open-ended questions left at this point. For starters, we just took a totally random data set and showed that, yeah, we can cluster into some values. Well, how would this do if we had an actual good data set? So you could either think about synthesizing some data, or by looking at some actual data, you could see how well it's doing. Second, we talked about different distance metrics. We used Euclidean distance here, but you could have tried Manhattan distance or some other distance. You get different results. What about higher dimensional systems? We used 2 to make our visualization simpler, but what if you had a higher dimensional system? Maybe you have 27 dimensions that you want to use for your clustering. How do you visualize that? How do you show that? How can we better visualize the boundary regions between these different clusters rather than just relying on where the points we happen to have are? So today's discussion was to serve as a jumping off point for implementing Kmeans and getting you to start asking these interesting questions about what comes next. Thanks for watching, and a special thanks to those whose donations help fund and sustain creating content like this. As always, the code produced today is available on GitHub through a link in the description. Remember to like, subscribe, push all the buttons, click all the things, and I'll see you next time.